Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. So today we are going to continue with chapter number 3, or particularly the sub-chapter of torque speed characteristic. And again, this is the equivalent circuit of the induction machine, and thus we try to emphasize on this region only. Okay, the secondary part of the induction machine or the induction motor. So again, we do have the V phase, we have the I1, we have JX1, so R1, and as well as the JSM. So now what happened here? So we try to analyze the Thevenin equivalent voltage plus the Thevenin equivalent impedance. Okay, so we try to disconnect at this particular part, okay, at E1 region, and from here try to come up with the VTH circuit as well as the TH impedance. So now this is the final equation of the Thevenin voltage. We have Xm over square root R squared plus X1 plus Xm squared. And then we have the Thevenin impedance over here, okay, GSM. So in bracket R1 plus JX1 R1 plus JX1 plus XM. Okay, so some of the derivation on how to obtain this relationship and also this formula. So now we start with here. This is the impedance of Z1. Okay, and then this is the impedance of Zm. And if you have this type of circuit, so we have a VTH over here and over here, and from here we are able to come up with this VTH. Okay? So we try to apply the voltage divider onto Zm, the magnetizing branch over here. So over Zm plus Z1. Alright. And then in terms of the resistance, also the reactance, so we try to expand the equation into more detail. We have VTH equal to V phase, so GXM over GSM plus JX1 all here, okay, here and here, plus R1. Okay, this is not 2 but 1. So we just consider the magnitude of the equation. So let me write here magnitude as for reminder. So we have VTH, so squared, this is equal to V phase, okay, squared, so JXM also squared, plus R1 squared plus X1 JX1 plus XM or JXM squared. So remember what happened if we have J squared. Okay. So since J squared, so we have actually here equal to minus 1 squared, and give J squared equal to 1. That means we have eliminate J over here, this J as well as the J. So Now what left? We just have VTH squared equal to V phase squared SM squared over R1 squared plus X1 in bracket XM and squared. Okay. To remove squared, so we have VTH equal to, okay, so we try to square root everything over here. So now we have V phase XM over square root R1 squared plus X1 plus XM squared. So here, the one I draw in box is equal to this one. So we are done with the derivation of VTH. Okay. So what about the Thevenin impedance over here? Okay. So now we have again the same VTH, or we use the same impedance of ZM. We try to simplify the equation. Sorry, to simplify the circuit over here. Again, this is the ZM, which is parallel to Z1. Okay. So ZM multiplied by Z1 over Z1 plus Zm. Okay. And so from here, so ZTH equal to RTH plus J X dot Z dot XTH. Okay. And thus expanding the equation, the above equation, so you may get JXM, okay, R1, okay, plus JX, X1, this is from Z1, okay, over R1 plus JX1 plus XM. Okay, so this is the final equation of ZTH. Same goes to this equation. Okay. All right, now next slide. So it says that since XM is much greater than X1 and XM much greater than R1, and X plus SM is actually much greater than R1, so thus VTH approximately equal to VXM over X1 plus XMV V phase. Okay, so now we have eliminate the element, okay, of R, because the value is much too small, okay, for the equation of VTH. So now we come to RTH. So this is approximately equal to R1 XM over X1 plus XM SM squared. Right. So this is we can derive from this actually from here the previous equation in the previous slide. Okay. And then we have XTH is approximately equal to X1. Alright, so this is again the equivalent circuit of the Thevenin voltage plus Thevenin impedance. And now from this circuit we try to implement KVL. Okay, let's say this is the loop. Okay, let's say this is the loop, and thus, so from the circuit, so VTH equal to I2 multiplied by ZTH plus Z2, and then rearrange in terms of I2, so you might get VTH over ZTH plus Z2. And again, what is ZTH? ZTH is actually RTH plus JXTH. And what is Z2? So go back here, Z2 is actually here Z2, these two elements, okay? Z2 is actually R2 over S plus JX2, okay? Here, R2 over S plus JX2. And then the magnitude of I2, so now we try to eliminate the imaginary part of the impedance, which is J. Okay, just like what we have done earlier in terms of the derivation. So to get the magnitude of I2, so now we have VTH over square root, okay, RTH plus R2 over S squared plus XH plus X2 squared. Okay, so you can try your own to derive the equation in order to obtain the magnitude of I2. So the A gap power, this is the equation, 3I2 squared R2 over S, and then in this particular equivalent circuit, the Thevenin's equivalent circuit, so we just substitute the value of I2 over here, okay, or the magnitude of I2 over here into this PAG equation. Okay, this I2, and don't forget to square it. Okay, here. So all this again, all this again into here, and thus you may get the final formula of the PAG, which is equal to 3VH squared R2 over S over blah 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 blah. Okay. So now the rotor-induced torque. So again, the formula, we have induced torque equal to PAG, the gap power over omega sin. Okay, so take the PAG equation over here, right, and put into this torque, induced torque equation. So that giving us the whole formula in this red box. Okay, so it's a very direct forward equation for you to use later on when we come to example or mathematical analysis. So now the typical induction motor torque speed characteristic curve. So what can we understand from the graph? So actually this is the induced torque shown in the percentage of full load. So 100% of the full load, 200% of the full load double, so triple, quadruple, blah 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 blah. So what will happen to the induced torque itself, okay, with respect to the mechanical speed, right? So now the starting torque over here at 0 speed, okay, the end scene is actually 0 RPM, okay. So we have about 200% of full load. I mean the induced torque. Okay, so we call it as starting torque. As the graph or the curve increase, okay, with respect to mechanical speed at this particular point, for example, so this is almost, we would say almost 40% of the speed of the end speed, sorry, the end scene, the synchronous speed. So we may get the pull up torque. Okay, so this is actually here, and the pull up torque. Okay, and then it reach up to the maximum peak of the torque or the curve, where we call as pull out torque. Right, it's almost 4 times of the full load, the induced torque at the full load. And before it decrease it goes down to zero. Sorry, at zero torque. Okay, here is a zero Newton meter at synchronous speed. So the full load torque always happen at this 100% okay of the here induced torque, and this is if you drag down, so you may get almost the end sync of the speed, of course with certain level of slip. So the certain level of slip at full load torque, that cause the speed of the machine or the mechanical speed is not up to its synchronous speed. Okay. So how about the particular curve? Okay, we have again the induced torque percent of full load, and then what happened actually if we try to increase the mechanical speed beyond it end sync, the synchronous speed, or 2 times the end sync. Okay, so we have 108,000 for example. This is just only for example. And then we have 2 end sync, we have 3,600, which is double the synchronous speed. Of course, the unit is RPM. Unit is RPM. Okay, so you can see here, this is the again the starting torque. So we have the pull up torque over here. So we have this is the pull out torque. So again we have the 100% over here. So the full load torque before it come to zero torque at and sync. And then again, what happen if we try to increase the speed even more? So if the rotor of induction motor is driven faster than end sync, okay, so it goes exceeding the end sync. So direction of induced magnetic field reverses, right? Then machine become, of course, become generator. Okay, so it start to generate electricity. Okay, so it seems like it's a mirror to the motor region. Okay. If you again increase the speed of the end sync. So power and torque converted versus motor speed. Okay, so we have a induced torque again over here. So in Newton meter at this first y-axis, and the second y-axis. Okay, we have the power in kilowatt. So the blue one is the induced torque. Okay, and then the red one is the converted power. The red one is yes, this is the converted power. As you increase the mechanical speed of the motor, for example, this is up to 1000 RPM, 1800 RPM. Okay, so here no more induced torque developed when Nm equal to N sync. So we can say that when the speed of the motor Nm, or the mechanical speed, reach up to N sync, so we can see that there is no more induced torque developed, as well as the power. Okay. So maximum or pull out torque. So maximum torque occurs when the air gap power is maximum. So the air gap power PAG is maximum. So this happen at PAG maximum. So remember, the condition of having the maximum torque or the pull out torque, and it is equal to the power consumed in the load resistor, which is R2 over S. Okay, if you refer to the equivalent circuit of the IM, so you may see that R2 over S is located at the most right of the circuit, which is the load resistor. So thus, so R2 over S equal to R square root RTH squared plus XTH plus X2 in bracket and squared. Okay, so this is the equation. Okay, this is actually from previous slide. Where is it? We can see here the previous slide Okay, over here, all over here. Okay, all over here. So next is sorry. So we have, yes, maximum power transfer to R2 over S, so the load resistor, when the magnitude is equal to the magnitude of the source impedance Z source. Okay, so this is again the equation from the previous slide. Z source equal to RTH plus JXTH plus JXX2. So these are the conditions in order to obtain the maximum pull-out torque. What about the slip at pull-out torque? So yes, this is nothing but from again the previous slide here. Okay, this one. All right, yes, this one. And we try to rearrange the equation in terms of S. You see, so S is located down here. So the denominator S, so rearrange, and then you will get that S max is actually equal to R2 over R3H squared plus blah 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 blah. And please take note that R2 is the only numerator here. Okay, so the above data here is the only numerator. Thus, slip is actually proportional directly to the rotor resistance. R2 is the rotor resistance. So we can say that S max is actually directly proportional to the R2, the rotor resistance. Okay. So about the pull out torque, so T max equal to VTH squared, blah 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 blah. So value of maximum torque here, the value of maximum torque is independent of value of rotor resistance. So you cannot say that the pull out torque is just similar to the S max that directly proportional to R2, but this is different. Okay, it doesn't actually dependent to R2 because we cannot even find any R2 value in this equation. So no R2 value. All right. So it depends on the VTH and also the RTH. So example number 4, 208 volt 4 pole. So number of pole. So we have the VT over here. And then we have the FE, the frequency. So we have the star connected induction motor is rated at 15 HP. So the 8 equivalent circuit components are R1, here R2, here Xn over here, X1, X2. And you need to calculate the slip at pull out torque, okay, the S max. So what is the pull out torque of this motor? The T torque pull out. And then let's see the solution over here. So we start with the equation, just a very direct forward analysis. So we have VTH equal to XM R1 plus JX1 over R1 JX1 XM. So substitute all the value. This is from question. Again, this is also from question. This is from question. So 0.22, 0.43, the value of X1. This is 0.1 or 15 ohms. This is the value of X1, SM, sorry. And then, so again, you may get this answer. So 0.470, 63.7 degree ohms. And then don't forget the unit. And then VTH again. So you may use this equation and then put in or substitute all the value provided in question again. And you may get that the Thevenin voltage is 116.7, 0.8 degree volt, okay, unit. And then the slip at pull out torque, so we have R2 over RTH squared, VXTH plus X2 and squared. So from here, you may get the value of S max is 0.145. Right. So what about the pull out torque, T max, okay, or the pull out, T pull out? So we have again the equation of 3 VTH square, 2 omega sin RTH square plus XTH plus X square. and then you need to square root everything here. Okay, and then remember, let me go back to the phase value over here. So I forgot one thing to tell you, so don't get confused. This is nothing but the V phase. Okay, so what should you do with the V phase? So we have over here the V line. Okay, so divided by square root 3. Okay, so we have 208. Let me show you from the question here. Okay, 208 volt divided by square root 3. Okay, this is giving us 120 volt. This. All right, and then here, come back to this equation. So what about the W or the omega sin? So omega sin, so it's come from N sin. Okay, so the N sin, because all the data of calculating N sin is provided in question. So what is the equation? So we have 120 F E over P. So this is the reason why the question provide you with this 4 poles, 60 hertz, blah blah blah, and also the Y connector. So the Y connector to tell you that the V phase here we are calculating here is unequal to V line. Dia tak sama lah. Right? It's different. Okay. This is the relationship. That's why you need to divide it by square root 3. Sorry. Okay. Due to the Y connected or Y configuration. So now back to our N sin. So we have our P over here. We have our FE over here. And from this, you might be able to calculate the N sin, the synchronous speed in RPM. So we have just now is how much? Sorry, 60 hertz. All right. So we have 60 over 4. Okay. And thus we have 1,800 again RPM. Okay. And then you need to convert to omega sin. Okay, so we have omega sin. So this is equal to, and see, just to make it short, so I divide by 9.55. Okay, so you have 1800 divided by 9.55. Right, so this is giving us 188.5. So radian per second. Okay, so this is the value of omega sin. The rest we have just calculated. So we have a VTH over here. We have RTH again. So XTH as well as the X2. Okay. And then finally, the pull out torque of the motor is 100 Newton meter. So now example number 5. So 2-pole 60 Hz induction motor supplies 15 kilowatt to load at the speed of 2950. Again, this is the P. So this is what? This is the FE. Okay. So we have the P load over here. Okay. So the multiply supply to a load. Okay, so we have the P load over here, 15 kilowatt at the speed of blah blah blah. So what is the rotor slips? So what is the induced torque? Okay, the induced under these conditions. So what will be the operating speed of the motor be if its torque is double? Okay, if the torque double, so how much power will be supplied? So P load will be supplied by the motor when torque is double. Okay, this is related to question C. So let's start solution number 5. The synchronous speed of the motor is, again, and sin equal to 120 FE over P. So set the value of frequency and also the number of poles. so giving us the NC equal to 3000 revolution per minute. So therefore, the motor slip is S equal to, so try to record the equation of S NC, which is NC minus Nm over NC multiplied by 100%. And then again, this is from question. So Nm is given in a question. So 3000, we just calculate over here the NC. Oops. And then from here, you are able to calculate the value of S, which is 1.6787%. So B, the induced torque, okay, in the motor must be assumed equal to the load torque. Okay. And P converted must be assumed equal to P load, since no value was given for mechanical losses. There is no any mechanical losses value. Okay, the losses, for example, and then friction and windage, for example, they are all not provided in question. So we assume that there is no any losses, mechanical losses, and thus the induced torque in the motor is equal to the load torque. Okay, and then what happened to the converted P? So equal to P load. So everything converted to mechanical load will be conveyed or will be transferred to the load. Because in between we have P converted, for example, again, let me write the flow chart or the flow diagram. So we have P load. So this is of course the load. So supplied by the shaft. In between, suppose we have two type of losses, for example, the mechanical losses, okay, PF and W. So we have the P, not R, but P to say, for example, these two are considered as the mechanical losses, since there is no any mentioned mechanical losses. So we can say that the P converted is okay, genuinely supplied to P load. Okay. And then the induced torque P converted equal to over omega m. So remember to convert 200 or 2950 RPM multiplied by 2 pi radian multiplied by 1 minutes per 60 seconds, or here actually equal to 9.55. I mean over 9.55. So this is giving you the final value of induced torque equal to 48.6. Okay. So now in the low slip region, so the torque speed curve is linear. So you can recall from the previous slide or the earlier slide of the video. So we see that at the low slip region, or the torque speed curve is actually linear, quite linear, and then the induced torque is directly proportional to slip. Okay, so therefore, if the torque doubles, then the new slip will be double too. For example, 3.33%. The operating speed of the motor is thus. So you can see from here. So since this is at low slip region, so this is very less, 1.67% or 0.00167. If you multiply or times 2, so this gives us 3.33% or 0.0033. Okay, because again, a low slip region, the torque speed curve is linear. Okay, it is directly proportional. Then we can say that if we try to double the value of torque, okay, here, this means we are also increasing the slips to double, okay, as well. And then Nm equal to I 1 minus S N sin. So substitute the value of 0.0033 multiplied by N sin is at 3000 RPM. So giving the new operating speed of the motor is 2900 RPM. So the power supplied by the motor is given by P converted equal to the induced torque omega m. So the induced torque omega m, so we have 97.2 Newton meter. This is from previous calculation. So again, here we have omega m, which is 2000, the new Nm divided by, here is actually the new Nm divided by 9.55. Okay, so this to convert into radian per second or the omega m. Okay, and then giving the P conversion equal to 29.5 kilowatt. Alright, thank you very much for watching. Hopefully you enjoy the video. See you around. Signing off.